All right. So I'm going to talk about expanding the horizons for LP, basically being able to solve new types of LP problems. Interest for this has actually been sparked recently by a paper from some folks at Google, practical large-scale linear programming using primal hybrid dual gradient. So the paper was published a couple of years ago. It actually builds on a technique, primal dual hybrid gradient, PDHG, from 2008. And then building on this paper, there have been a few papers that talk about implementing this approach, PDHG, on a GPU. The intent of this work and other work has been to expand to what's possible. So in order to understand, where this fits in the landscape, we need to compare it against some of the other approaches. At a high level, comparing PDHG against the alternatives. So there are a few significant positives. The main one is that it parallelizes very well. In particular, it parallelizes well on GPUs. So the primary computation is a sequence of sparse matrix vector multiplies, where the matrix is your constraint matrix for your LP, and then a set of dense vector operations. And these have tons of parallelism. So GPUs are all about parallelism. The other thing GPUs are about is massive memory bandwidth, and PDHG, this algorithm, relies heavily on memory bandwidth. So again, a very nice match. So GPUs typically have HBM, high bandwidth memory, and the bandwidth is typically 8 to 40 times faster than CPU memory. I'll provide some data later. And the big negatives for PDHG. So the first negative is the solutions are generally low accuracy. So you get less accuracy than you do for the alternatives. So the typical default for PDHG is a 10 to the minus 4 relative tolerance, whereas with barrier and simplex, with the alternatives in Gurobi, the default is typically a 10 to the minus 6 absolute tolerance. So there's quite a big difference in tolerances. Another negative is PDHG seems to be quite sensitive to parameters. So you make a few changes, the number of iterations can change by factor 10 or more. Simplex is somewhat sensitive to parameters, barrier much less so. And then PDHG, it often fails to converge. There's some models where you can run it, no matter how many iterations you do, it just never finds the solution. So, PDHG is a way to exploit parallelism. So there have been other approaches to exploiting parallelism in LP. So looking way, way back, so Irv Lustig and I in 1996 published a paper, Gigaflops in Linear Programming, about using a barrier solver on a modestly parallel CPU. And when I say modestly parallel, 16 or fewer cores is kind of typical. And if you look at where the opportunity for parallelism comes in barrier, it mainly comes from the sparse Cholesky factorization. So the time for a barrier solver is typically dominated by this step. You have to solve linear systems in order to get direction vectors. And typically the most effective way to solve linear systems is to do a Cholesky factorization and then a set of triangular solves using the results. And this factorization, it actually also parallelizes quite nicely. And as a result of this, as the number of cores in CPUs has grown, the performance of barrier relative to the performance of simplex has grown as well. And it's probably just a result of the fact that it can exploit parallelism where simplex cannot. So if we're looking at expanding frontiers, then an obvious question is, how far can this parallelism that we're already exploiting in barrier, how far can this be pushed? So in order to understand that, we need to understand what the important steps are in the algorithm. So I've listed 5 here. These are the main ones. There are others. So there's a pre-solve step where you take the user model and you reduce it to a smaller, hopefully simpler model to solve. There's a sparse matrix reordering step. This is a step that is meant to reduce the cost of the factorization. There's the factorization itself. And then there's the step computation. This is the part of the computation where you use the result of the factorization to compute direction vectors. So these are the steps of the barrier algorithm itself, and you do several iterations of barrier, you get a interior point solution. So you get an optimal solution that is very, very close to the optimal face. And typically, the barrier algorithm is followed by a crossover step, where you take this interior solution and you turn it into a basic solution, so a vertex solution. In the computation here, it's basically a less complicated version of simplex. It's simplex with a few steps essentially skipped. So if you look at the parallelism opportunities for the various steps in the barrier solver, so the opportunities vary depending on the step. So for the factorization, there's tons of opportunities to exploit parallelism. For the computing steps and doing sparse matrix reordering, there's some parallelism. And then for pre-solve and crossover, very, very little. So there's some, but very little. So how does this play out? So if you look at a breakdown of where runtime is spent in the barrier solver for a variety of models. So I just took our standard LP test set. And here I'm just looking at the models that take more than 100 seconds to solve. So there's 199 models in this set. And I ran this on a 16-core CPU, an AMD 7313P. And this is the percentage of runtime across this full set of models that's spent in pre-solve, ordering, factorization, all the different stages of the optimization. And what you can see is the effect of having 16 cores. So the factorization, which on one core would be the dominant computation by far, it's been pushed down to a point where it's actually no longer even the top consumer runtime. So the crossover step, the sequential step here, essentially is the largest cost in solving ALP using the barrier method on a 16-core machine. And as I mentioned, the crossover step is optional, so you don't have to do the crossover step. And if you don't, then the majority of the time is in factorization or computing steps, both of which have quite a high degree of parallelism. So you may look at this and say, well, these are models that take more than 100 seconds. That's not that large. What would happen if you looked at harder models? And so here are results for models that take more than 1,000 seconds to solve. There are 46 models are considered here. And what you see is that crossover becomes even more important for these harder models. So, and again, if you remove crossover, so if you skip the crossover step, factorization dominates with the step computation second. So there's significant parallelism to be exploited here, but there are also some potential caveats, the crossover step. All right, so now let's take a look at the scope of opportunity from PDHG. So, and what we're going to do is we're going to try and compare the scope, compare the performance of PDHG against the performance of barrier, an interior point method, just to get a sense of where PDHG has potential scope for doing better. And the way we're going to do this is we're just going to look at the dominant costs for the interior point solver and for PDHG. For the interior point solver, as I mentioned, the dominant cost is the sparse factorization, and you can measure the cost just by counting the number of floating point operations that are required to perform the factorization. And then essentially multiplying that by the number of iterations that are typically performed in a barrier solve. And that number is typically around 100. There's some variation there, but it's typically around 100. So for PDHG, the dominant cost is a sparse matrix vector multiply. And the matrix you're using is the A matrix, the constraint matrix. And so a simple metric for predicting the cost of an iteration is the number of non-zeros in A. And multiply that by the number of iterations. How many iterations? Well, it's hard to say, but I'd say order 10,000 is generally a reasonable estimate. So if we're looking at comparing the cost of the interior point solver versus the cost of PDHG, we can get some sense of what the relative cost is going to be by looking at the ratio of the number of factorization ops, the number of operations required to perform the Cholesky factorization for the interior point method, divided by the number of non-zeros in A, which is basically the cost of doing the sparse matrix vector multiply for PDHG. And we can plot these numbers. So here's a scatter plot. So on the x-axis, we have the number of non-zeros in the pre-solved A matrix. And on the y-axis, we have for each model, we have the number of operations, floating point operations for the factorization divided by the number of non-zeros in the matrix. And each point here is one model from our LP test set. So there are 2,576 points on this plot. And thing to note here is as the ratio of number of operations for the factorization divided by number of non-zeros, as this ratio increases, the scope for improvement for PDHG increases as well, because the barrier relative to PDHG is getting more and more expensive as you rise on the y-axis on this chart. So you can reasonably ask where the crossover is. Basically, at what point would PDHG likely be faster than barrier? And I've included a bunch of computation at the bottom of this slide. I'm not going to go through this in any detail. Basically, I'm just trying to get a ballpark estimate for when the barrier solver is just going to be potentially a lot more expensive than PDHG would be. And if you go through the computation, which again I'm not going to go through, basically what it tells you is that in order for PDHG to have significant scope to do better than barrier, we would need to be above this line. And you can see that there are quite a few points above this line, but the majority of points are actually below this line. So among the models in our test set, most of them probably aren't going to see a benefit from an approach like PDHG, but some definitely are. And I should point out a limitation in this methodology. So these are the scatter plot here. Each point is a model that is in our LP test set. And in general, people formulate models that they can solve. And generally, we keep models that we can solve. So if it's in our LP test set, it means we can solve it. And so the models that we can't solve, in general, aren't in this graph. So, bottom line, so the PDHG probably not a lot of scope for the broad set of models that we solve regularly, but there are definitely significant number of models where there is some scope, and there are probably models that aren't in this set where there's potentially even more scope. All right, so I talked about scope for improvement from a model point of view. Now I want to talk about scope for improvement from a computing point of view. Basically, what can we get from applying faster, better computing resources? And before I start with that, I have a bit of a bone to pick with a few of the recent paper and a recent blog post talking about PDHG. So PDHG, generally the PDHG is evaluated using the latest and greatest GPU, and then it's compared against various alternatives running on CPUs. So one recent paper compared PDHG running on the latest and greatest NVIDIA Hopper CPU or GPU, and compared it against an AMD Ryzen 9 5900X. And if you look at look at the internet, this is a desktop processor, $500, released November of 2020. And there was a recent blog post that compared PDHG running on the latest and greatest GPU against AMD EPYC 7313P, which is a server processor, 16 cores, that was released in March of 2021. So, here we are comparing the absolute fastest, most recent GPU against CPUs that are, fairly low end, 3 or 4 years old. So if our goal is to evaluate what it's going to take to push the boundaries of what's possible with LP, we should be doing it using the best possible computers for the alternative techniques, given that we're using the best computer for the GPU approach. All right, so to give you a bit more context here, so let's look at the advantages of a GPU just in a general sense. I'll start off just comparing it against a modern desktop CPU. And you can look at this using two different metrics. So the first is just raw floating point performance. If the processor is running flat out, what's its rate of performing floating point operations? And the second is memory bandwidth. If you're pulling data from memory, how quickly can you pull that data? So comparing the NVIDIA GH200 GPU, 34 teraflops of floating point performance, if you look at the latest AMD Zen 5 desktop 16 cores, 2.6 teraflops of floating point performance. So more than a factor of 10 more performance from the GPU. On the memory bandwidth side, so as I mentioned earlier, the GPU has HBM, high bandwidth memory, and you can pull about 4 terabytes a second peak from memory. Whereas on the desktop CPU, 90 gigabytes a second, so more than 40 times more memory bandwidth. So those are some big numbers. But if we broaden the context a bit, so adding in so I added in 2 processors on the left here. So the first is, so the latest NVIDIA GPU system, the Grace Hopper system, includes both a GPU and a CPU. And so, these are, of course, the same technology, the same vintage, because they're in the same machine. So this is a 72-core machine. It produces about 3.5 teraflops of floating point performance. But this is actually not the absolute fastest CPU you can get right now. That appears to be the AMD EPYC 5. You can get it with up to 190 cores, 192 cores. Just looking at the 128-core version, this produces about 23 teraflops of performance. So about 2/3 the performance peak of the GPU. And then on the memory bandwidth side, more recent processors indeed have higher bandwidth than desktops, more recent server processors. So the Grace CPU and the Grace Hopper system, 384 gigabytes a second. EPYC has 576, and then even actually Apple, the M4 Max, has 546. So, but if you compare that to the GPU is still factor of 7, factor of 8 faster. So still some pretty significant scope for improvement. All right, so these are abstract numbers. These are peak numbers. So what can we actually expect to see for LP? So to look at this, we need to actually take a look back. So if you ask for a particular application, what the performance is likely to be on a particular machine. So there's this long-standing historical distinction among applications. So some applications are memory bound, meaning their performance is limited by the speed at which you can pull data from the memory system. Some applications are compute bound, meaning basically the performance is limited by the speed of the processors, how quickly they can process computations. And there are benchmarks for each of these. So memory bound application, the benchmarks are stream and HPCG. And if you look at the LP algorithms, so PDHG actually looks almost exactly like HPCG. And so PDHG is very similar to the canonical memory bound applications. So for compute bound applications, I'd say the prominent benchmarks are LinPack and HPL. And if you look at the barrier solver for LP, the sparse factorization looks very, very similar to LinPack. And so we can actually get a sense of what to expect for these LP algorithms looking at fairly standard benchmarks. So here's some benchmark numbers that I gathered. So these come from actual measurements on actual machines. And what I'm trying to gather here is the benefit that comes from using different machines to solve an LP using PDHG. And I'm actually looking at I'm measuring this in iterations per second. So how many iterations can each of these machines plow through in 1 second? And I'm using one particular model, ZIB01, for this tested. Truth is, the results didn't vary that much from model to model. And what you see here on the far left, we've got an AMD Ryzen 9900X. So this is a modern, fairly inexpensive desktop processor with a fairly modest memory system, 90 gigabytes a second. And you see that the number of iterations per second for PDHG, if we go from 1 to 2 cores, it rises, 2 to 4, rises again, and then 4 to 8, 8 to 12, it's pretty flat. And we top out at about 9 iterations of PDHG per second on this machine. And so what's happening is basically we've got a pretty modest memory system, and you can throw as many cores as you want at this memory system. Memory system is saturated. So 9 iterations per second is all you can get from this memory system. So if you move up to the NVIDIA Grace CPU, this is 72 cores, 384 gigabytes per second of memory bandwidth. So this is a much more powerful memory system. And you can see, we top out, instead of 9 iterations per second, we top out at 55, say. And you can also see that the memory system saturates, but in this case at a much higher point. So once we get to 40-some cores, we've saturated the memory system. That's the maximum we're going to get. And then by contrast, if you look at the Hopper GPU, the GPU in the Grace Hopper system, we get about 450 iterations per second on for PDHG on this model. So that's about a factor of 8 faster than what you get from the CPU inside the same Grace Hopper system. So that's quite a substantial difference. Okay, on the compute bound side, if you look at these machines, and I added another to the mix. So the first numbers I'm going to show you are just the performance, the throughput you get for doing matrix multiplies on each core. So they're not coordinating at all. They're just doing independent matrix multiplies. And here we have, again, performance for the Ryzen 9 9900X, the desktop chip, on 1 through 12 cores. And we top out at about 1 trillion floating point operations per second. On the NVIDIA Grace CPU, we top out at about 1.5. On the EPYC, the 96 core, the absolute, probably the fastest CPU right now, we top out at about 4.5. And on the NVIDIA GPU, we top out about 34 teraflops. So actually, one thing I want to point out here, which maybe contradicts something I said earlier, is that, so I described these matrix multiply and LinPack and such as compute bound. But in fact, the number of cores and the capability of each core have gotten so strong over the years that even traditionally compute bound applications are still actually a bit memory bound. And so the reason these flatten out is because they've saturated the memory system. So even if you're doing a very cache friendly, a very memory system friendly application, it's likely your performance is still going to be constrained by the capabilities of the memory system. And then if you look at improvements from the Grace CPU to the Hopper GPU, factor of 23, so huge potential improvement from the GPU. And then the EPYC to the Hopper, about a factor of 7, still a nice improvement. But of course, matrix multiply, in doing these independently on multiple cores, it doesn't really capture the performance of sparse factorization that accurately. So let me look at actual sparse factorization numbers. So what we have here are 5 different models. These are just models that are chosen to have difficult factorizations. And then we have on the y-axis, we have performance in gigaflops. And the red bar is the Grace CPU, and the blue bar is the Hopper GPU. So these are the CPU and the GPU that are in the Grace Hopper box, the NVIDIA Grace Hopper box. And the factorization in the case of the CPU, this is our standard barrier factorization code. And in the case of the GPU, so NVIDIA has released a library, cuDSS, Cu Direct Sparse Solver, for doing sparse factorization on a GPU. And you can see the GPU is quite a bit faster than the CPU. So, 3x, 4x, 8x, in one case, almost 11x faster. And on average, for these models, comparing the GPU to the CPU, around 4.5x. So not the 8x we saw for PDHG, but still a pretty significant opportunity for improvement from the GPU. So let me add the AMD EPYC system. This is using 64 cores. As you remember from the previous slide, basically we've saturated the memory system beyond 64 cores, so there's actually no benefit going beyond 64. And you can see that the EPYC is actually quite a bit faster than the Grace CPU, about a factor of 3. So the GPU will often have a significant advantage, but geomean over the 5 models here, about 1.5x. So still a nice improvement, potentially a very large improvement depending on the model, but on average, not nearly as large as for the Grace CPU. All right, so those are our opportunities for parallelism from, looking at it from a model point of view and looking at it from a machine point of view. So how are we actually going to exploit these opportunities? So we're actually going to look at 8 different approaches to exploiting parallelism, to solving these LPs. And they're going to be based on a few different approaches, a few different codes. So the first, of course, is PDHG. So we've done an implementation of PDHG for the CPU, so multi-threaded on the CPU, and we've also done a GPU implementation. And our implementation mirrors the implementation from the 2021 Google paper. And again, as I mentioned earlier, the performance is determined by the speed of the sparse matrix vector multiply. So it's basically determined by the speed of the memory system. So these have been integrated into Gurobi 12.0. We haven't released this yet. We haven't released a GPU version. We're working on it, so that'll happen at some point. Okay, so the next option we're going to consider, of course, is just out-of-the-box barrier. So parallel Cholesky factorization within barrier. The code we're using here, it's basically the same barrier code that we've had for 15 years. We know the factorization scales well to 32 cores. Most of the other steps in barrier scale fairly well, but as I mentioned earlier, there's some exceptions. Truth is we don't really have that much experience with scaling it beyond 64 cores. So as I mentioned, this is our out-of-core barrier. In looking at how it scales on larger machines, we actually did make a few changes. We made a few improvements. So it's a slightly better version of our traditional parallel barrier code. So the other option we consider is, since we're doing factorization and there exists a library for doing factorization on a GPU, so, let's look at performance for barrier using the NVIDIA cuDSS library. And again, this is integrated with Gurobi 12.0, but it's not yet released. And then the last option is an iterative solver inside barrier. So if you look at the factorization inside barrier, the point of doing the factorization is to solve linear systems in order to get direction vectors. And when it comes to solving linear systems, there are 2 general approaches. There are direct methods that use factorization, and there are iterative methods, things like conjugate gradient or conjugate residual. And there's been lots of interest in the past in using iterative solvers within the barrier method. One nice property of iterative solvers is they have lots of parallelism. So if you look at the parallelism in an iterative solver, it's basically exactly the same as the parallelism in PDHG. So you're doing sparse matrix vector multiplies, dense vector operations. We should expect pretty much exactly the same behavior when it comes to GPU. So historically, when it comes to using an iterative solver in barrier, there have been 2 main problems. So problem number 1 is the solutions you get just aren't as accurate as the solutions you get with the direct solver. And problem number 2 is on a lot of models, the iterative solver just fails to converge. These are serious issues, but at the same time, these 2 problems probably sound familiar. These are exactly the problems that people cite when talking about PDHG. So there may be scope to go back and re-examine iterative solvers within barrier. And our version 12 of Gurobi includes a parallel iterative solver. And it's actually triggered automatically. So if we look at a model and we determine that there's scope for using the iterative solver, we will just use it automatically. But we also have some hidden options that basically just force you to always use it. So I should add one nice property of the iterative solver within barrier is that the iterates they're what's called well-centered. So basically they're they're desirable, they create desirable points for starting a barrier solver, for continuing a barrier solver. So that means that we can actually smoothly transition from using the iterative solver to using a direct solver at some intermediate barrier iteration. And as best as we can tell, the same is not true for the iterates from PDHD. You can't take an iterate from PDHD, hand it to barrier, and expect barrier to be able to make good progress from that iterate. All right, so now I've talked about the different methods we're going to consider, but before I actually show any performance numbers, I need to say a few words about tolerances and convergence. So, if you're going to compare two methods, basically you have to ask, well, what exactly are they doing? Is it an apples to apples comparison? And when it comes to PDHG, one of the very important decisions that have to be made is, when can you stop? When is your solution accurate enough? And the reason you have to make this decision is PDHG is linearly convergent versus barrier, which is locally quadratically convergent. And I could write down the definitions of these two terms, but I figured it'd be better to show the difference in a figure. So these are results from a model THK63. On the x-axis, we have runtimes in seconds. And the y-axis, we have the largest violation, whether primal, dual, or complementary. So a truly optimal solution would have 0 violations in all three. And what you see is as time progresses, PDHG makes slow and steady progress on all these violation metrics. Barrier, on the other hand, makes fairly modest progress, and then it gets close to the optimal solution, and then the progress is extremely fast. So, and that's the locally quadratic convergence. So once you're close to the solution, in a few more iterations, you get a solution that is as accurate as machine precision allows. So the practical implication here is that for barrier, when it comes to termination, there are no decisions for you to make. So basically, you just let barrier run until it's finished. And the difference between that and trying to stop it early, in terms of runtime, typically not that big. Whereas for a first order method like PDHD, you actually have to decide when you're going to stop. And so what's an appropriate termination criteria? Well, ultimately that depends on the user. It depends on the person who's actually solving the problem. And you may say, well, if I've got control of the termination criteria, it's fine. I know what sort of accuracy I'm looking for, but you don't actually have that much control. And one of the main reasons is that the model that is being solved by the solver is not the same as the model that's being presented by the user. And the two main reasons are pre-solve and scaling. So the user presents us a model. We apply pre-solve to reduce the size and hopefully difficulty of the model. We apply scaling to improve the numerical conditioning of the problem. And then we hand that problem to the solver, simplex barrier PDHG. And the termination criteria is applied on that problem. We get a solution that satisfies that termination criteria. Then we apply unscaling to unscale that solution, and then unpresolve to undo the presolve, which leads to a solution that we can present to the user for the original problem. And each of these steps, the unscaling and the unpresolve, introduces additional error. So let me quantify that. Here's a model, PDS 100, multi-commodity flow model. And on the x-axis, we have 4 different approaches for solving the problem. We have PDHG with a 10 to the minus 4th relative tolerance, a PDHG with a 10 to the minus 6th relative tolerance, barrier without crossover, so the final iterate of the barrier solver, and then a basic solution, a basis. And on the x-axis, we have the primal residual, the norm of the primal residual, in absolute infinity norm of the primal residual. And so here we have a PDHG with a 10 to the minus 4 relative tolerance. So we've gotten a solution that satisfied that. The red bar here shows what happens if you just change the criteria from a relative tolerance to an absolute tolerance. So in absolute terms, for this model, the violation is 10 to the minus 1. The first blue bar is after unscaling. What happens to the residual after unscaling? It increases by a factor 10, so 10 to the 0. And then after uncrush, the error is larger than 10.0. So we've taken a 10 to the minus 4 relative tolerance, and it's turned into a 10.0 violation of some constraint on the original model. And we can tighten these tolerances. So 10 to the minus 6 relative tolerance, all these numbers come down, but we're still talking about a violation of 0.2 on the original model. And then, if you look at the barrier, as is probably expected from the previous slide, the errors are very small. Applying unscaling and uncrush increases them somewhat, but still, the final error is 10 to the minus 9. So, many, many orders of magnitude smaller. And then with the basic solution, basically you get, the smallest error you could possibly imagine. So 10 to the minus 13 error. So similar results for a different model for RWTH timetable. So let me take a step back, say a few more words about termination tolerances. So when it comes to barrier and simplex, the termination tolerance is, and pretty much always was, the infinity norm of B minus AX. So the largest violation of any constraint in absolute terms. And the magic number that has been used for probably 40, 50 years is 10 to the minus 6. So we're looking for a 10 to the minus 6 largest violation of any primal constraint, dual constraint, complementarity, what have you. At PDHG, what's emerging as sort of the traditional termination criteria is the relative 2-norm tolerance. So the 2-norm of B minus AX divided by the 2-norm of B. And, as is probably apparent, this can be a lot bigger than the absolute tolerance. So, obvious question, what's an acceptable tolerance? And, as a solver vendor, my answer is it's not up to me. So really, it's up to the user what tolerances are acceptable. And I suspect the reality here is that we just don't have a lot of experience with the trade-off between runtime and solution quality. So I'm not even sure that users know at this point what acceptable termination criteria are. But one thing I do know is if you think about the relative tolerance, so intuitively you may say, well, 10 to the minus 4 relative tolerance, that sounds pretty good. So, if the solution is close to optimal, maybe a 10 to the minus 4 relative tolerance means that you get, 3 or 4 digits accuracy for all of your for all of your variables. But it doesn't mean that. So consider a simple example. This is an extreme example. But let's say you've got a model with 1 million constraints that all look like xi plus xj less than or equal 1, where the x's are not negative. And then you've got one constraint, call it a capacity constraint. You've got continuous variables y1 and y2, and the sum of the two is less than or equal to 10 to the 7th. So that 10 to the 7th is in the right-hand side. It goes directly to the norm of B2. So if you do the math, a 10 to the minus 4 relative tolerance for a model that has these characteristics allows you to return a solution that satisfies tolerances where the capacity constraint is satisfied and every single one of the 1 million rows xi plus xj less than or equal 1 is completely ignored. So that's an extreme example. So let me look at a few more practical examples. So if you look at model Pilot S, this is a well-known LP benchmark. You find a solution with a 10 to the minus 4 relative residual, and you look at where that solution violates constraints, and what you find is there's a constraint C855. Looks like this. The x variables have pretty modest values. The right-hand side is minus 1.8 roughly. And this constraint is violated in this 10 to the minus 4 relative residual solution by 0.4. So a 10 to the minus 4 relative residual produces a 22% violation of this constraint. And then similar model, similar metrics. So PDS 100 network flow model. You've got flow conservation constraints. So the flow into a node is equal to flow out of the node. In this particular example, at 10 to the minus 4 relative residual, the flow through this node is 372. The constraint violation is 13.5. So 4% more flow leaves this node than enters this node. So is that acceptable? I don't know. But I mean, my gut feel is it's probably not. So my gut feel is that people just need higher quality solutions, tighter tolerances. So, what does that mean for PDHG? Well, it probably means that PDHG, the solutions also need to be fed into something that looks like crossover. And crossover is routine in barrier. You can shut it off. Very few people do. The fact that PDHG produces solutions with substantial errors, well, barrier sometimes produces solutions with non-trivial errors. And so crossover codes have been built to handle this. There are limits, of course, but they can deal with some error. All right, so having said all that, now let me give some performance results. So as I mentioned earlier, I'm going to show results from 8 different options. And the first 5 are all going to be on the same CPU. So apples to apples comparison between these. And the CPU is going to be the 72-core Grace CPU on the Grace operating system. We're going to run barrier with the Cholesky factorization and with an iterative solver. And then we're going to run PDHG with 10 to the minus 4, 10 to the minus 5, and 10 to the minus 6 tolerances. So that's 5 different data points. And then we're going to switch machines. We're going to run barrier on the absolute latest, greatest 96-core CPU. And then we're going to run barrier and PDHG on the GPU. And as I mentioned earlier, these are all our own implementations run on machines where we actually did the runs. So these are all measured results with actual code. And then when it comes to the models, so as I mentioned earlier, so we're trying to expand the frontiers here. And so taking a model where it's, we already know that it's easy to solve doesn't really tell us what we're probably looking to figure out. And so, we've chosen a set, anecdotally, we've just chosen a set of models where existing methods struggle. And in fact, we've chosen models that have been mentioned in papers about PDHG. So these are models that seem difficult, and other people seem to agree are difficult. So some results. So lots of data in this chart. Let me tell you how to read it. So basically, each bar here shows the runtime to find a solution to this model. In this case, model RWTH timetable. And the different bars show different algorithms and on different machines. So as I mentioned, the first 5 are all running on the Grace CPU using barrier with a factorization, barrier with an iterative solver, and then PDHG with 3 different tolerances. And then the next bar shows barrier on the fastest CPU we can find, barrier on the GPU, and then PDHG on the GPU. The red bar shows the time required to perform the iterations. So the barrier iterations, the PDHG iterations. And then the green bar shows the time required to start from the solution that is produced by either barrier or PDHG and perform a crossover to a basic solution from that point. And so what you can see here, so on the 64 Grace cores, this model took, call it 800 seconds to solve, with the vast majority of the runtime going to the barrier iterations. About 13 seconds went to the crossover. So difficult model. So the iterative solver unfortunately failed to solve the model. The barrier didn't converge. PDHG, if you use a 10 to the minus 4 tolerance, the time to actually find a solution that satisfies the tolerance is incredibly quick, 10 seconds. However, the crossover is quite expensive, so 560 seconds from that point. So if you need to do crossover, and it's optional, you don't have to do crossover, but if you need to do crossover, it's going to be expensive from this point. As you tighten the tolerances, so the time required for PDHG grows, but doesn't grow that much, from 10 seconds to 10 to the minus 4 to 20 seconds to 40 seconds. But what you see is the time required to do the crossover, makes sense. drops. So you're giving crossover a better starting point, and so it just takes less time. And then when it comes to barrier on the latest and greatest CPU and on the GPU, recall that on the GPU, so this was the model RWTH timetable where the GPU gave a factor of 11 performance improvement versus the Grace CPU. But as I mentioned earlier, this was just for the factorization. There are other things in the barrier solver that don't parallelize as well. And so this 11x on the factorization translates to closer to 2.5 or 3x on the overall barrier solve. So a few conclusions to be drawn from this. First off, barrier definitely benefits from having a faster CPU or a GPU. So these two bars here are quite a bit smaller than this initial bar. And the crossover time depends heavily on the quality of the starting point. So the time for crossover drops significantly as we tighten up the convergence criteria for PDHG. And overall, for this particular model, PDHG is a huge win compared to any of the alternatives. So PDHG on the GPU, the iterations go faster, but they're already so fast that doesn't have a huge impact. All right, so here are results for a different model, a model grid 10. So on this model, actually, the barrier solver didn't have that much trouble solving at about 190 seconds. So the iterative solver was able to solve this model quickly, but the crossover didn't converge. For PDHG, we see a similar pattern. So as we tighten the tolerances, the time for crossover decreases, but the time for the iterations, of course, increases, and the increase in the iteration cost dominates the decrease in the crossover cost. So in this particular case, you're actually best off with a weaker convergence criteria. And then in this case, the GPU is actually a bit slower than the CPU. So that can happen. And then the GPU for PDHG gives a really nice improvement compared to the PDHG running on the CPU. So, bottom line here is that so having a more accurate start for PDHG doesn't always pay off. It's really a trade-off in the cost of the PDHG iterations versus the cost of the crossover. And GPU barrier, it's typically faster, but not always. So here are results from model ZIB01. Not going to go into much detail here. One thing I did want to point out is that here's a case where PDHG with a 10⁻⁴ tolerance, the crossover just doesn't finish, doesn't complete. The solution is just not a good starting point for crossover. Whereas 10⁻⁵, 10⁻⁶, crossover finishes relatively quickly. So the crossover from PDHG, it can be fickle. So basically, you need to choose the right termination criteria in order for crossover to succeed. So here's an example, RMIND 25, where for PDHG, the crossover is just expensive. Crossover alone from PDHG takes more time than crossover plus the barrier iterations running on the CPU. And so this is an example where basically, so for some models, you just need an extremely accurate start point. And so the fact that barrier gets, 9, 10 digits really comes in handy on this model. And then finally, model THK63. Here we have multiple different options, all giving pretty similar performance. So in some cases, basically, there are actually multiple different ways to solve the problem, multiple different good ways to solve the problem. And one thing I wanted to mention quickly, so that, when it comes to the PDHG results, so the fact that in some cases you want a more accurate solution to get a smaller total runtime. In other cases, you actually want the less accurate solution to get a smaller runtime. So this, sort of leads pretty naturally to an idea, which is, as you're iterating with PDHG, maybe it makes sense to just fire off a thread to do crossover. And then continue iterating, maybe fire off another thread, continue iterating, fire off another thread. So basically you use parallelism to actually explore different approaches, different strategies for crossover. So conclusions. So one conclusion is when it comes to convergence criteria, I think PDHG is probably the first algorithm that puts tolerances front and center. So you as the user have to make a decision about what's appropriate, what's an appropriate termination criteria. This really is not a user decision for simplex and barrier. So what's acceptable accuracy? Well, as I mentioned earlier, it's not for me to say. Ultimately, it's up to the users. But the users, as I mentioned earlier, don't necessarily have so much control over this because unscaling and unpresolve will typically degrade the tolerances that the user specifies, or degrade the solution, often making it worse than the tolerances that they're after. So if PDHG is going to be an effective general purpose method, we're probably my prediction is we're probably going to need something like crossover to get to a basic solution or solution with higher quality. And the issues here, so crossover is highly sequential. And if the starting point has substantial violations, crossover can be slow. And this whole if crossover is in the mix, then this tolerance question gets pushed even more to the front. Because at this point, the user isn't deciding what tolerance they're willing to accept. They're deciding which tolerance crossover is willing to accept. And that's a tough question. So I suspect that there's significant opportunity here for new algorithms, new approaches to thinking about crossover and just getting more accurate solutions from a PDHG iterative. All right, having said that, it's great that there's a new horse in the race. So, PDHG has gone from a paper to a method that's competitive on, a small set of models, but potentially an important set of models. And the fact that it's so new means the technology is still evolving quickly. And the fact that it sometimes wins, sometimes loses against the more traditional approaches, we're used to that. So if you look at the state of the art for solving LPs now, basically we fire off primal simplex, dual simplex, and barrier on multiple threads, mainly because we don't know which one's going to be the best. And so we exploit parallelism, we exploit concurrency, take advantage of the fact that we have all these options. So having a new option, it just gives us more flexibility. And so there's quite definitely the possibility that this can open up new classes of models to be solved. So the GPU is a 10x opportunity, clearly. And this is true for both PDHG and also for barrier. But it's a 10x opportunity for something. That something doesn't necessarily translate to a 10x improvement in the time to solve the problem. So this is an early attempt to exploit GPUs for solving LPs. It's still early. There are going to be more opportunities. So this will only improve. So conclusions. It's great that there are new options for solving giant LPs. The fact that each has its strengths and weaknesses, we're used to that. So, just the fact that we, have a new option is, it's all positive. It's all great. And the accuracy issue, so the fact that PDHG introduces this really strong trade-off between speed and accuracy, this is new. This is something we're going to have to get used to. But it seems that, once we do get used to it, there are going to be significant opportunities here. So, any questions?
All right, thanks, Ed. I guess we can jump in with some of the questions from the audience. I guess one of the questions that I'll ask now is about related to crossover. So we had several people asking this, asking various questions about crossover, and you've actually highlighted that in some of your later slides. So you answered some of the questions. But I think, I guess, first a clarification. People are curious about when you showed the GPU results and you talked about crossover. Was this crossover on the CPU of the Hopper? That's one question. Yeah.
Yeah. Oh, yeah. Yeah.
Yeah.
No, the crossover there's very little parallelism in simplex and crossover. So yeah, it would be very hard to build a GPU version of crossover.
Yep. Good. And then I guess the other related question, I think it seems like you've also highlighted this as kind of a key challenge is the accuracy and the crossover. So do you, I guess, have any guesses or any intuition about where the opportunities might be? Maybe trying to find more accurate solutions from the primal dual methods, or trying to rework crossover in some other ways to try to help it converge faster.
Um, I mean, I think this is an opportunity just to rethink the whole notion of crossover. So, I mean, crossover was Nimrod Megiddo wrote this beautiful paper, basically showing that if you had you know, an exact optimal solution that wasn't necessarily a basis, the crossover procedure would give you a basic solution in polynomial time. And basically the whole basis of this is an assumption that you're starting off with an optimal solution with perfect accuracy. And so, if you relax that, do you necessarily wind up with the same algorithm, or are there opportunities to just rethink some of the aspects of what it does? I don't know. I think there's an opportunity to fundamentally rethink what it means to do a crossover.
All right, thank you.
Yeah, so I have a different question here from Lawrence Legg. And if you could comment on the potential speed up of using a CPU-based Cholesky factorization, like the one available NVIDIA processor within the barrier method.
CPU. So we do. So all of the results that I showed used a parallel Cholesky factorization for the CPU.
No, I mean potential speed up on GPU-based Cholesky factorization.
Yeah. So all the GPU results
Yes.
use GPU-based factorization. So maybe I'm missing the intent of the question, but I think all the results that I presented that were labeled GPU came from a GPU-based factorization.
Right. I mean, the question was posed in the context of comparison with the CPU-based Cholesky factorization. Okay.
Yeah. So this is the factorization and the solves running on the GPU. And this here is the factorization and the solves running on the CPU, both in parallel, both on the same box, basically within the same physical box. So this is parallel GPU versus parallel CPU. That is the comparison that was done here.
Right.
Don't know if that clarified.
Yeah.
Okay. I'll ask the next question. And again, several people have been asking this. I think there's just a lot of curiosity about what is available right now in Gurobi 12 and when we might expect to see some of these other things available for use from the user's side.
Right. Right. Yeah. So we have no GPU binary. So none of the GPU methods are available in a release. And we've got it running internally. So, I mean, frankly, if you've got a giant LP model, you're curious whether any of these approaches might be relevant, send it to us. We'll be happy to run them. We've got a latest and greatest GPU machine. We've got machines with 72 core CPUs with 72 cores. When are we going to release this? Soon. I'm not going to make any promises, but we're definitely working hard to figure out how to turn this into something we can release.
All right, thanks.
So I have a question. If you could dream of a ideal CPU GPU architecture purpose built for solving LPs and MIPS, what would it look like, and how would this differ from what vendors offer today?
Yeah, it's an interesting question. Yeah, so this is probably my only foray into the world of trying to push things beyond modest parallelism. So I've learned a lot in the process, but I can't say that I've learned enough. So unfortunately, I think it's still premature for me to render an opinion on what I would change. mainly because right now I think the main thing to change is my getting a better understanding of what's possible with the existing architectures, the existing machines. So I'm dodging the question, I know, but unfortunately, I don't think I have a good answer. Not yet.
All right, I'll ask another one that we've again seen a few times. So the topic here is really about solving large LPs. Of course, people are also asking about, about the implications for MIP. So I just wonder if you have anything to share, beyond maybe solving the initial LP relaxation faster in some cases, about opportunities for GPUs in for solving MIPS.
Yeah, that's a tough one. I mean, so like, general purpose MIP solving, that's going to be hard. Applying GPUs to, specialized phases of the computation, maybe, but at the same time, it's not so clear that if you just apply it to a specific phase, that will have a big impact on the overall time to solve the problem. So I don't know. I mean, we're so far from being able to exploit a GPU to really hit at the meat of the MIP problem that I think it's going to be tough.
All right.
Okay, I think we have time for one more question. Is a parallel iterative solver in Gurobi version 12 using a preconditioning based on the factorization?
No, it's not. It's very simple. It's just using a diagonally preconditioned conjugate residual. I mean, once you start doing factorizations, then there's not much reason to have an iterative solver. And you can talk about there are various techniques like let's see. Anyway, there are various preconditioners that stop short of a full factorization, but then typically you lose parallelism. So what we do is very simple. And actually, it still works fairly well on some models, but it's very simple.